Hey everybody, I am going through 14.3 notes now, energy and chemical reactions. So still looking at chemical reactions, but we're going to look at some specific types, kind of not necessarily like the types we just learned about, but we're looking at the energy that is involved in chemical reactions, and reactions that gain energy, lose energy, things like that. So with today, we have our essential question: how does energy influence chemical reactions? And then we have three learning targets. One is the difference between exo and endothermic. We need to know both of those. We need to know ways to increase or slow down the rate of a reaction. And then we need to understand what chemical equilibrium is. So first things first, exothermic reactions. Exo, that prefix exo means out, like an exoskeleton is a skeleton on the outside, right? So exo means out, thermic means energy. So we have a reaction that gives out energy, forming new bonds, releases more energy than it takes to break the old bonds. Energy is a product and it gets hot. Okay, so important thing there: energy is considered a product. Okay, so that means that it is given off in the reaction. That's kind of a key indicator with an exothermic reaction, is that energy is produced. These are reactions that give off heat or light, like a fire. A good example of an exothermic reaction is the reaction of hydrogen with oxygen. Oxygen combines with hydrogen and we get water, and it also gives off energy to do that. Notice over here, energy is a product. Sorry, energy is a product. It is produced in this reaction, meaning it is an exothermic reaction. Once started, exothermic reactions tend to keep going very quickly, as each reaction releases more energy to fuel the neighboring molecules. What that means is, like, if I'm going to start a piece of paper on fire, I don't need to put a lighter to the entire piece of paper to light it all on fire. I can light one corner of that paper and that fire will spread to the rest, because the energy that is being released is going towards breaking the next molecule, the bonds in the next molecule, and we'll explain that more in a little bit. Endothermic is the other type. Okay, an endo, if we have an endoskeleton, our skeleton's on the inside. Endothermic reactions take energy in, therefore energy is a reactant, and things get colder. An important endothermic reaction is photosynthesis. You guys learn this. You guys have seen this for sure. 7th grade, 100% you have. But if we are going to go through photosynthesis, plants take in sunlight, right? Sunlight is a form of energy. So we have carbon dioxide and water, and sunlight is needed to make that glucose and oxygen. We have to have that sunlight present. Otherwise, the plants will not go through that chemical reaction. They need to take in that energy first. Energy, notice it's a reactant in this reaction. Energy is a reactant. It goes in. That means that this reaction is an endothermic reaction. Now, activation energy. You guys notice that you can't just start a fire out of nothing, right? You have to put in that energy first. That energy that you put into starting that fire is your activation energy. Energy needed to begin a reaction and break chemical bonds. Okay, so if you look at this, hydrogen gas and oxygen gas are bonded together, right? Atoms bond together to reduce their amount of energy. Hydrogen gas is at a lower energy state when it combines. Hydrogen is at a lower energy state when it combines with another hydrogen to make hydrogen gas, right? Same with oxygen. We don't want single oxygen atoms floating around. They're going to bond with something else to reduce their energy level, and that's good. But they would rather have an energy level down here, just like you guys on a Saturday. You don't want to have an energy level super high. You want your energy down low, right? You want to reduce that amount of energy. My toddler, if he's got a lot of energy before bed, I got to find a way to reduce that energy. So we have to find a way to break those chemical bonds, and we can do that by putting energy into the reaction. Maybe it's a little bit of electricity. Maybe it's sunlight in the case of photosynthesis. Or maybe it's that spark that you need to light that paper on fire. And then once we give it that activation energy, that energy needed to now notice the hydrogen molecules are broken and the oxygen atoms are broken apart. Okay? Now they don't want to stay like that. They want to be at their lowest energy state. So oxygen combines with hydrogen, reducing that energy. When it does that, it gives off a lot of energy, and that energy goes towards breaking new bonds and doing this whole process again. So this is why a flammable material like gasoline does not burn without a spark or a flame. So here again, we have hydrogen molecules in yellow and oxygen atoms molecules in green. And here we have some electrodes, and you're going to see that when a spark goes through there, we get some electricity running through there. That's energy, and that's the energy needed to break the chemical bonds holding together the hydrogen and the oxygen atoms. They break those bonds. Do those atoms want to stay apart? No, they want to combine to make, notice these atoms are now water. And what do you notice about the atoms right next to those ones? They're broken now. These atoms have all broken just like these ones were. Well, what do you know is going to happen with those atoms being broken? They're going to then combine into water and release more energy, breaking the other molecules around them. That's what happens with a fire, and that's why you don't need to light the entire piece of paper on fire. You just light one corner, and it goes and spreads and breaks the rest of those bonds, reducing that so that they can form new bonds, reducing that energy. Endothermic reactions, most of the reactions used in industry to produce useful materials require more energy than they produce. So if they require more energy than what they produce, they take in more energy than what they give out. Energy is then a reactant, and that makes it an endothermic reaction. Okay, so endothermic reactions are very common. Here's one example: aluminum oxide and energy. It requires energy to decompose into aluminum and oxygen. Another example of an endothermic reaction is this instant cold pack. You squeeze the plastic bag, the water reacts with ammonium nitrate crystals, and the reaction dissolves the ionic bonds in the ammonium nitrate, and that is what is actually happening. So if you've seen those ice packs where it's like you need to like puncture the bag inside, there's water in there. That's really what you have. So with that water, then you have these ammonium nitrate crystals, and when they combine, it's taking in that energy, it's taking in heat from around it. Okay? And that's really like if you think about icing your shoulder or something like that, if you put one of these ice packs on your shoulder, all it is that energy that your shoulder and that your body is producing is going towards that chemical reaction that's occurring there. It's taking the energy away from your shoulder, cooling your shoulder off, allowing stimulating some blood flow so you can heal up a little bit faster. Reaction rate. So what we're moving to now is the second learning target, the rate of reactions. And what we're going to look at is ways that we can increase or decrease a reaction rate. Okay? Ways that we can make a chemical reaction happen faster. Right? And you guys have seen some similar things before. For example, like if you are going to dissolve sugar in water, well, you stir it up and it happens faster, right? So that's the type of thing that we're going to talk about. So ways to increase the speed or the rate at which a chemical reaction happens. One way is to heat it up. Okay? If you make your water hotter, it can dissolve that salt or sugar faster. What I like to think of here, so how does this happen? How does heating something up actually make it happen faster? Okay? I like to think of chemical reactions happen when atoms or molecules come in contact at the right time in the right location, right? So when they make those collisions. Now, let's imagine that you're in a classroom and you have 20 people in a classroom, okay? And you're just walking around normal speed. Anytime you go by someone, you give them a high five. Cool. Now let's add heat to you. What does that mean? You get more energy. When you get more energy, you are moving faster. Remember, temperature is the average kinetic energy per molecule. So if we raise the temperature, it means that you guys are all moving faster in that room. The faster you move, the more collisions, the more high fives you're going to give to each other. Okay? That means that your reaction is happening faster. The same thing happens with atoms and molecules and substances. The faster they're moving, the more they are able to react with those elements around them. So adding heat makes things move faster and speeds up that reaction. The other thing that we can do is now, instead of having 20 people in the classroom, let's make it so we have 60 people in the classroom. By increasing the reactants, we can increase the chances of those reactions happening faster. If there's more people in the room, you're more likely to bump into someone to give them a high five, right? And then the next one is stirring. Similar to adding heat, it's kind of making those molecules, those atoms, move faster. Thus, they're going to have a higher likelihood of coming in contact with another atom or molecule in the right way, meaning that chemical reaction can happen. So ways to increase all revolve around making those molecules move more and coming in contact more. Adding heat, adding reactants, and stirring. The only one that doesn't is this guy here, a catalyst. Okay, a catalyst is kind of like that spark plug. It can get something going. A lot of times, if you're a baseball or softball person, they might refer to the leadoff batter as like the catalyst for the lineup. They're the spark that gets things going. A catalyst is a molecule that we use to speed up that reaction. And a catalyst works by increasing the chances that two molecules will be positioned in the right way for a reaction to happen. We take molecule A and molecule B, and we put them together, and that increases the chance that they will happen. So here's another simplified way of explaining a catalyst. Let's say that, you know what, there are two students that they're going to eventually form a relationship. They're destined to be together. You can see it. They don't know each other super well, but you know that they're going to make a good pair. Well, we can just let them go through high school and they'll come in contact more. And we know because of destiny and because of fate that they're going to end up together. And that may take time and it will likely happen, or maybe they just never come in contact. What we can do is say, hey, you know what? You two, you guys are great together. You don't even know it yet. I'm going to put you guys together. And then we can speed up that reaction. We can make that reaction happen faster by putting them in the same environment, in the right position for a reaction. If they're not going to react, they won't. A catalyst doesn't make things react. A catalyst helps things react quicker. It puts them in the right spot for a reaction. That's what a catalyst does. The opposite of a catalyst is an inhibitor. So we can say, hey, you know what, guys? I see you two are starting to talk a lot. Like a teacher could do this in a classroom. I see you two are starting to talk a lot, and you're not really benefiting each other in the classroom when you're doing that. So what I'll do is I'll put you in the back corner, you in the front corner, and limit that interaction or inhibit that interaction, right? So an inhibitor makes it so that molecules or the reactions slow down. They don't happen as quickly. An inhibitor is just something that blocks that chemical reaction from happening. The last learning target is chemical equilibrium. One important thing to kind of think about with chemical reactions is that, like, here's an example. If we're going to make water, well, we need hydrogen gas and oxygen gas, and when they react, we can get water, right? Now, what about if we have water? Well, that water can break down to produce hydrogen gas and oxygen gas, right? The reaction can go both ways. So chemical equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. That means that water breaks down just as fast as water is produced. Basically, for us, we don't see any difference. In chemical equilibrium, the reaction can proceed both left and right simultaneously. The reactants and the products, the concentrations never change. We don't see this reaction happening. It's in chemical equilibrium. Here is a picture of that. Okay, so here we have an arrow. This is kind of how we typically do it. We say, okay, A plus B gives us AB, right? This could be hydrogen gas, and oxygen gas gives us H2O. It could also happen the opposite, though. We could have this side be the reactants. Water, H2O, gives us hydrogen gas and oxygen gas. Chemical equilibrium is when they're both occurring at the same time. And remember, when that is happening, we do not notice it. That is when we do not see the chemical reactions happening. They're proceeding left and right simultaneously, the concentrations of reactants and products do not change. Okay, so that is kind of that's the last thing there, chemical equilibrium. All right, that's all I have for you for this section of notes. Don't forget your section review questions. Have fun. Ask questions if you have any, guys. Thanks. Bye.